Okay, I want to welcome everybody to the August 2019 University of Texas Speaker Series. Got a great presentation for you today. I want to introduce Bartley Estes, and Bartley has a bachelor degree from the East Central University in cartography, focusing specifically on geotechniques. He's been the last 8 years with remote sensing efforts at CEC Corporation, and is also a American, the ASPRS, the American Society of Photogrammetry and Remote Sensing, as a mapping scientist specializing in LiDAR technology. Today we're going to have a great discussion on LiDAR platforms and emerging trends. And Bartley, go ahead. I'm going to turn it over to you, and thank you again for being here today.
Sure. Thanks, Brian. So before I even get started, I want to say thank you to Janie and Brian and Danielle and Ollie for reaching out and giving me the opportunity to present today. I am honored to be able to present to the group. Brian, thanks for the introduction. I mean, you pretty much hit it all, hit the nail on the head. But yeah, a little bit more about me. I am pretty much just a big geospatial nerd. I love technology. My background is obviously in remote sensing and GIS, but specifically the company that I work for, CEC Corporation, we are a engineering firm, so infrastructure engineering firm. And so that's where a lot of my frame of mind is from the engineering world. But I understand we have a lot of folks here today that don't necessarily operate in that space. So my goal today is to introduce everybody to LiDAR, just in general, what the technology is. If you have no idea what LiDAR is, that's totally okay. We're going to start with the absolute basics, and then hopefully introduce you to the different platforms, because LiDAR technology inherently operates on the same principles, but there are many different platforms. It comes in many different shapes and sizes. So what I want to do is introduce everyone to the different platforms, what makes them similar, what makes them different. And so what I would like for the group to do is to think critically about the kinds of projects that you work on specifically. And as we explore the differences between the different LiDAR platforms, you can start to think about what platform, what kind of LiDAR could best suit your project. And hopefully at the end, we can have a great discussion on different kinds of projects and what is best suited for them. LiDAR technology inherently is just a data collection tool. So it is broadly applicable across many different fields. And so one of the things that I also want to touch on is the data that it produces, commonly known as point clouds, is really enhancing the way in the geospatial world how we can leverage data. Basically, in the conventional mapping or the conventional survey world, the main goal was just to map something out and say what it is and where it is. But the amount of data that we're able to collect with multiple geospatial technologies, but specifically LiDAR, we can do a lot more than just tell what something is and where it is. There's a lot of applications that we can apply it to. And then the last thing that I want to talk about is some emerging technologies in the geospatial world. We'll talk about drones, specifically some new innovations in the LiDAR world, and just some things that are on the cusp of being integrated into the everyday workflow, but are just starting to emerge into the field. So to get started, just in case nobody knows what LiDAR is at all, we'll just jump in at the very beginning and I'll kind of explain what the technology is and how it works. So first of all, LiDAR is an acronym. It stands for Light Detection and Ranging. It is a technology that works very similar to like sonar. If you think about sonar, sensor will send out a sound wave. That sound wave will reflect, and you can map like the bottom of a lake. LiDAR works essentially the same way, just instead of using sound, you're using pulses of light or lasers. And what makes these sensors very powerful is many times these sensors can generate a million pulses or more every second. And so with it working very similar, if anyone's familiar with survey technology, like how a total station works, it works very similar to that, but on steroids. So it's shooting out these lasers a million times every second. Every laser is recording a point, a coordinate, latitude, longitude, elevation, and some additional information. And because it's collecting so many points per second, what you end up with is a point cloud. It's a common term for a LiDAR data set. And so some of these photos that I'm showing, they may look like 3D renders or photos, but these are of actual LiDAR data sets. And they're each of these point clouds is comprised of millions of individual points, which every single one has a X, Y, and Z. And in some of these photos, you can see like this one that we're looking at here is colorized by elevation. So the high points are red, low points are green. But what LiDAR will do, because we're using pulses of light, it will also capture the reflectivity value known as intensity values. And that's why we can, on the roadway, like that crosswalk there, we can see things like the striping and why concrete looks different from asphalt. Because inherently all of these things have different reflective properties. So when we're looking at a LiDAR point cloud, because we are getting those intensity or those reflectivity values, it helps your brain, kind of understand the scene that you're looking at. It lets it makes a lot more sense. So that's LiDAR 101. That's how the technology works. And what I want to do is break it down into the different platforms. So like I said earlier, LiDAR technology comes in many different shapes and sizes, but inherently it operates with the same principles. It just depends, what kind of sensor you're using and basically what you strap it on. So the most basic form of LiDAR is called terrestrial LiDAR, sometimes called static LiDAR. And this is just a sensor that sits in a fixed position on a fixed height or a tripod. And these sensors many times will rotate in 360 degrees so that it scans the entire environment all the way around the sensor. Now, terrestrial LiDAR is considered many times the most basic form of LiDAR, but it is arguably also the most accurate. Because you are collecting this information from a fixed position, that means there's no motion in the process. There's no GPS. There's the sensor isn't moving, and so that removes a whole level of error from the equation because the sensor is collecting this information from a fixed position. So that gives some flexibility in the terrestrial LiDAR data acquisition in that it is the most accurate. And so it is a lot of times preferred for architectural or structural as-builting. So things like bridges or an architectural project like a building. Obviously, because because terrestrial LiDAR is on a fixed position, you can do things like take it inside of a building. You can map, the entire floor plan in 3 dimensions of an entire building. So terrestrial LiDAR is it's the simplest form, but it is many times the most accurate, and it you're getting a lot of points. So you're getting a very high level of detail and very high accuracy. So I do have some photos here of some examples. And before I go on, I do want to say when we get to the next section after we talk about LiDAR platforms, we'll talk about exploiting LiDAR data. And I've got some screenshots, and I want to touch on how, as users, as people who consume data, how you can exploit this data in software packages that you may use every day at work. But anyway, moving forward. So I've got some screenshots here of some LiDAR data sets. And you kind of start to get a feel for the amount of precision and comprehensive data collection that it's capable of picking up. One thing that I will point out here, I think I do have a quick video, is if you have an area that you're trying to scan with terrestrial LiDAR, you are collecting it from a fixed position, and lasers are affected by line of sight. So if you're standing where the sensor is and you can't see it with your eye, the lasers aren't going to see it either. So something like we're looking at here, like this power plant, where we were tasked with doing an inventory of all of the piping network and documenting all of the assets on this power plant. It took multiple setups, so you can see there's some gaps there on the ground. It looks like a blank circle on the ground. That's where the sensor was set up. And so to collect a site like this, where there are multiple sight lines, you have to kind of leapfrog around and do multiple scans from multiple locations just to make sure that you're covering all of your sight lines. So if you're tasked with a project like this, where you're really trying to not only document what is included in this power plant, but being able to exploit the data and be able to model from it, where okay, well, we know there are pipes here, but what are the diameters of all of these pipes? Where does each pipe enter and exit the ground? And the footprints of all of the buildings and things like that. You kind of have to make sure you get a complete picture of the site. So that's terrestrial LiDAR. So let's talk about mobile LiDAR. This is what I am most familiar with. Mobile LiDAR is really what I cut my teeth on in my career. But given the realm that I work in engineering, we do a lot of transportation projects, and so we really benefit from mobile LiDAR. Again, it is the mobile LiDAR sensors operate just like any other LiDAR sensor. It's slinging out those 1,000,000 points per second. The only difference is now we have strapped it onto a vehicle and we're driving down the road, and it's scanning the environment as we drive down the road. So I've got a graphic here that it kind of shows how the data is collected around the vehicle. The only thing I don't like about the graphic is that it looks like it's only scanning in this small globe around the vehicle. Most LiDAR sensors can scan up to anywhere between 500 and 1,000 feet from the sensor, so you're collecting much further than this graphic is showing. But one thing that I mentioned with terrestrial LiDAR is there's no GPS and there's no movement involved. Well, that changes when we introduce LiDAR sensors to a vehicle. Now you're introducing motion, which means you're integrating things like GPS values and the trajectory of the vehicle, and what happens when the vehicle drives under a bridge and it interrupts that GPS receptivity. And so there are additional, and I won't go into the nuts and bolts of a mobile LiDAR system, but there are additional components to the equipment that helps justify that those new parts of the data that you have to account for. So mobile LiDAR systems will have multiple GPS receivers on them. they'll have things called IMUs, which measure inertia. So as the vehicle gets bumped around down the road, you've got the sensor in a fixed position, so that sensor is getting shaken around. So you got to have something to compensate for the inertia that the sensor is under. And so there's multiple components that are accounting for these external forces that the sensor is undergoing, and they do a really, really good job of accounting for that information. So here's a fly through of a data set that we collected with the mobile LiDAR system. And when you really think about, as it flies through here, for our purposes, for this project, it was for a topographic survey. And as it starts to fly around here and you start seeing the intricacies of these corridors of not just bridges, but flyovers and flyovers over flyovers. When you look at that from a mapping perspective, or you look at it from even a conventional surveyor's perspective, it's pretty daunting, because this project site has so many details. There's so many nooks and crannies and details, and not to mention it's dangerous, right? There's a ton of traffic in this project area. So thinking about tackling a mapping project or a asset management coming from that mindset, or topographic survey mindset, it's just daunting to think of a project of this size, not only from the detail point of view, but a safety point of view. So what mobile LiDAR allowed us to do here is to drive down the road. Obviously, not all of the lanes, but the majority of the lanes were driven with the mobile LiDAR system. And what you're essentially doing, and this isn't just mobile LiDAR, this is LiDAR in general. What you're doing is you're collecting the field in a very accurate format. You are collecting almost the entirety of the field, and that allows you to take it back to the office, and then you exploit the data from your desk. Whether you're a designer or a surveyor, working in Autodesk Civil 3D or MicroStation, or if you're a GIS user using Esri products or QGIS or Global Mapper, whatever you're using, these programs have become so robust in the last few years that they're handling LiDAR data. And now you're just able to exploit that information from the comfort of your desk, and not having to pound the pavement, so to speak, to collect all of that data. So that's mobile LiDAR. So quickly, let's touch on aerial LiDAR. Aerial LiDAR has been around the longest. Like most technologies, specifically mapping technologies, it was born out of the military, and in the recent years has been released into the market, civilian market. But aerial LiDAR has, within aerial LiDAR in general, it has multiple levels inside of it, and it's very flexible. So there is a graphic there on the right showing the different kinds of aerial LiDAR, and not all of them included on that graphic, but it kind of depends on your project, right? What is the goal of your project? Are you trying to have a very high detailed contour drainage map, like a DTM of a county? We're doing a county-wide mapping project, and then you're probably going to use a manned fixed-wing aircraft that's flying at a high altitude that can cover a lot of ground in a short amount of time. But if you are mapping a transmission line corridor where you're really looking for intricate details on transmission towers, and you need lots of points on the transmission lines, then you're probably going to use a helicopter where you can fly low and slow and at a lower altitude along that corridor, so that you're picking up more information and higher detailed information as you fly. One thing that I like to point out when I talk about aerial LiDAR is the differentiators between aerial LiDAR and traditional aerial photogrammetry. Because we've all used photogrammetry for years. We all know that you can generate a pretty dang good DSM or DTM from conventional photogrammetric data. But one thing that really sets it apart is because we are using laser pulses. Without going into too much of the science about it, basically, lasers can penetrate vegetation. I'm sure many of you have seen on like the Discovery Channel or the History Channel or whatever it is, they're recently discovering lost civilization archaeological finds in the Amazon. And that's directly from aerial LiDAR project. With the density of the rainforest, mapping with conventional photogrammetry, we've never been able to really see the terrain underneath the rainforest. But now that we have aerial LiDAR technology, we're penetrating that vegetation, and we're really getting a good look at the topography of what's underneath there. And so in the conventional photogrammetric data acquisition world, it's usually always a good idea to fly in the wintertime in what they would call leaf off conditions, so that you're minimizing as much vegetation as possible. But aerial LiDAR is not affected by that. You can fly 365 days a year. We are getting really good bare earth models from aerial LiDAR data collection, and that's due to that the splitting of the laser pulses where we are penetrating that vegetation. So I have a good example here of a test that we did internally using our own aerial LiDAR systems and photogrammetric payloads. And what we did was we wanted to compare the surfaces of the same area against hard surfaces that are not vegetated, and surface vegetation, so things like grass and then like tree cover. And so I've got some examples here of those two data sets. And what we're looking at in the top there is a plan view of an area that we flew with LiDAR and photogrammetry. And the bottom there is a cross-section of that data showing the two data sets. So the blue being photogrammetry, the red being LiDAR. And so you can see in the channels there where it's a hard surface, it's packed dirt, those two surfaces align almost perfectly. But in the areas that look kind of fuzzy, that's grass. And so you can see the red there, the LiDAR is slightly lower than the blue. And that's because when photogrammetry is doing its reconstruction and it's building that 3D DSM, it can only build to what it sees, and it sees the top of the grass. So that's what it's building to. Whereas LiDAR is penetrating that grass, so that's why it's slightly lower. So if it's really important to you to get a very defined DTM of the actual terrain, a bare earth model, LiDAR can greatly benefit there. And again, here's just another example. The blue there being photogrammetry, and red and a little bit of green being the LiDAR. We're in a tree cover environment. In the middle, in the red there, you can see there was a whole creek bed that had we generated this DSM, the surface model using photogrammetry, we would miss what could be a very critical surface feature, which would be that creek bed. So I always like to point that out because there are many projects where photogrammetry is just fine. It is just fine for that project. But I want you to think critically about the kinds of projects you work on, and if the bare earth model is really, really important to what you do, exploring aerial LiDAR and comparing it against conventional photogrammetry may be worth considering. I already touched on the different platforms, so the fixed-wing aircraft, manned rotorcraft, and even drones now. So that's a new area that we are moving into. Is just like any technology, like cell phones. It's always getting smaller, more compact, faster, better at what it does. And over the last 5 years, the same thing goes for LiDAR. The sensors are getting better, they're getting more accurate, and they're getting smaller. And so now they are small enough where we can start leveraging things like UAVs or drones to collect that information. So I do have, again, a quick fly through here. This is a data set that was collected with a drone, aerial LiDAR. And this is where, we sat down and we thought, thinking critically, okay, what is the best tool in the toolbox for this project? The goal of the project was to map the amount of sag on this wire as it crosses the river. And so for a transmission line project that wasn't a 20-mile project, it was 5 or 6 spans, is it really worth mobilizing a manned aircraft to fly 5 or 6 spans of transmission line? And so we utilized an unmanned system with a LiDAR sensor, and we collected all of this information in a 6-minute flight. And it was way more cost effective. It was faster, and we got the data that we needed by thinking critically about the project needs and what platform makes the most sense for our project. So that was a quick, I understand, is a very quick and broad overview of the different LiDAR platforms. But again, the technology it operates the same way, but depending on the platform, it can really help or hinder your project data collection. So essentially what I want to do is just get everyone thinking, one, is LiDAR applicable to your kinds of projects? Is this level of data collection applicable to the work that you do? And if it is, now armed with the knowledge of the different kinds of LiDAR, okay, what makes the most sense for your type of project? So the next thing that I want to jump into is the going beyond where. Okay, we've talked about LiDAR platforms. Now let's talk about the data that it collects. Let's talk about point clouds. So I mentioned at the top of the presentation, we're really graduating in the field from not just telling or not just mapping something and saying what it is and where it is. We're collecting a wild amount of data now, and as GIS users, this is where we're going to start to see a marriage between LiDAR data collection and GIS, because keep in mind, LiDAR is a data collection tool. That is what it is. It is collecting geospatial data. And so there is always a need of how do we take this data and exploit it for it to be usable, right? Because there are many in the design world and the infrastructure engineering world, we're getting to a point where we can leverage point clouds just in their raw format for our projects. But there are many times where the end deliverable is not a point cloud. It's a CAD drawing, or it's a surface model, or it's shape files or a geodatabase. So there has to be a connector between LiDAR data collection and information management, right? So GIS or modeling in a CAD environment, there has to be a connector there. So what I want to do is introduce you to some of the ways that we are seeing the benefits utilizing LiDAR data and creating in deliverables, but then also kind of pose it to you, the GIS community, of how can we leverage this data and manage it in a smart way, and utilize it in a format that is usable and can be integrated in in the day-to-day process in the projects. So as I get started here, I'm going to do my best to quickly introduce you to some of the applications that we are utilizing mobile LiDAR, or not mobile LiDAR, LiDAR data in general for, and hopefully spark some thoughts for you all on how you could possibly use it. So first and foremost, one of the thing, this is something we do all day, every day. Again, coming from that engineering background, is utilizing LiDAR data for topographic survey and as-builts. So we have all used, we're all used to, for years, using ortho photos, like aerial images, as references, whether it's in a GIS environment or it's in a CAD design environment. LiDAR can be utilized the same way. Like in the engineering world, many times a designer will say, LiDAR data is awesome, these point clouds look great, you've collected everything, but to do my design, I need a CAD drawing. I need my triangles, my surface models, I need contours, I need break lines. And so what we can do, and many different platforms can handle this, whether it's Civil 3D, Autodesk products, Revit, MicroStation. All of them have really come around in the past couple of years of being able to integrate directly these point clouds as references, and then you can extract from that your crucial data. So I've got some screenshots here. You can see the point cloud is in there as a reference, but we have generated, using the point cloud, a highly dense surface model. You know, we're not talking about conventional survey where we're doing 100-foot cross sections with 100-foot triangles. You can do 1-foot triangles. You can do 6-inch triangles. So you can have a very detailed surface model with very detailed break lines, while still pulling out all of those topographic features that are needed in the design process. But by using LiDAR, we're creating a much more comprehensive survey where we're no longer dealing with 50-foot cross sections, 100-foot cross sections. We are generating a highly detailed surface model that designers can use automatically. They can just they treat it just like they would any conventional survey, and they're integrating that right into the design process. The next thing is quantities and volumes. So again, we kind of talked about being able to generate a very detailed surface model using LiDAR. So I've done a little bit of movie magic here in the top screenshot with the right half showing kind of an isometric view of the point cloud, and then the left half showing the surface model that we generated from it. So many times in like construction projects or design projects, quantities are very important. Believe it or not, dirt is very expensive. And so as dirt gets moved around, you have to quantify that. And so what we're doing with LiDAR now is, before construction, going and scanning the project, and then as construction phases go through, we're scanning it as the construction phases go through. And so we're capturing the surface in that point in time. So at the end of the project, or even along the project, we can quantify to a very detailed specificity of how much dirt got moved and what is the topography really looking like right now. And so again, going back to that, it's been done conventionally with conventional land survey where you're getting an elevation every 100 feet. Well, you can see, just in the left side of that screenshot, there's a lot of detail in a ditch. There can be a lot of detail. And so having more points and more triangles means a more detailed surface model, which leads to more detailed quantity numbers. And here's just another screenshot, talking about quantities, things like stockpiles. So if you have a giant pile of sand, and you are a conventional surveyor, the last thing you want to do is try to climb to the top of that pile of sand to get a GPS shot. So again, being able to use laser scanning to capture in very, very high detail stockpiles is only leading to more defined and much more accurate quantity numbers. Clearance analysis. So this one is kind of a no-brainer, right? But we are utilizing it it's really helping with being able to do this work in bulk. And safety. So let me touch on that a little bit. So bridge clearances at a state level, we've worked with the DOT here, and the conventional way of getting a bridge clearance is really kind of eyeballing it and using a laser measurer to get that minimum clearance. And by doing so, you've got to get out in traffic, and that's not necessarily the safest thing in the world. So what we started doing is collecting in mass, in doing many bridges in one mobilization, is using mobile LiDAR to go collect the entirety of these bridges, and then back at the safety of our desk, we can exploit the data and not only pull measurements where it's required. So for this specific contract, they wanted clearances over each stripe. Software now is smart enough to recognize what's a beam and what is the pavement, and it will automatically generate for you the absolute minimum clearance. So there's no eyeballing it in the minimum clearance extraction. The software is recognizing it and plotting it and measuring it for you. Pavement condition analysis. So this is where we internally have really started to see a nice marriage between LiDAR and GIS, and I'll explain why. So because LiDAR is picking up so much data on the pavement, we are able to use software that will read that pavement. Let me see, I can't remember if I zoom in. Yeah, zoom in, okay. So you can run, a profile. What is considered a perfect road down that corridor, down the pavement, and it will colorize the points based on how bad the actual road surface deviates from that quote-unquote perfect road. And so that's really it's really changing the way that we approach doing roadway condition analysis, because really we're graduating from just someone an opinion, right? Somebody we call it a windshield survey. You drive down the road, somebody who, an engineer maybe who knows a lot about roadway condition, rates it 1 through 100. They give it a grade based on what it looks like. Well, we're graduating from that into real hard data that we can use to grade the roads on a consistent against a consistent rubric. And here's where that marriage happens between LiDAR and GIS. So we got these colorized point clouds. It's showing us where the damaged parts of the road are. But to go one step further, in the top left picture there, you see it's broken it up into tiles. It's generating these tiles, and it's kind of hard to see, but each one of those tiles has emblems in it, and each emblem has a color. Well, those represent the health and the the damage type of the roadway for that tile. I think they're 10 by 10 or 12 by 12 foot, I can't remember, tiles, but each one of those tiles is not only getting its own individual health rating, but it's documenting the kind of damage that exists, whether it's a pothole or just rutting, etc. And then also giving a quantity number of that damage. And so those tiles and those emblems and the data associated with them are exported as a shapefile and live in a geodatabase that can be pushed out. We ended up pushing it out to a live web map where there's this, it's not real time, but a consistently updated, this was a citywide project, health condition of the roadway in a GIS format that's hosted online. That was really something else. And so that is a very unique application, but we're really seeing a marriage there between LiDAR and GIS. Change detection and monitoring. The example I've got here is a retaining wall. We talk about temporal data collection. So there was concern that this retaining wall was actively failing. And so we scanned with mobile LiDAR, we scanned this wall once a quarter for 2 years to monitor it, to see was it changing over time. And so we did that, and I'm happy to tell you that the wall was not actively failing, but we did find some interesting things. So I'll show you here. It's kind of difficult to look at if you don't really know what we're looking at, but I'll do my best to explain it. On the far right-hand side there, we're looking at a cross-section of that wall. So conventionally, if you were going to measure a wall, whether it's failing or not, you get a coordinate at the bottom of the wall and the top of the wall. And so what you end up with a straight line between top and bottom. But one thing, and I'm going to go back a slide here, is that we discovered is on the bottom view there, we're looking at it side on now. You can see kind of a blue hue there in the middle. And so one thing that we found was if you just measured the top and the bottom, there are many places where the wall looked straight vertical and it would have looked just fine. But in between the bottom and the top, there are areas where there were panels on the wall that were bulging. And so if we had collected that data using the conventional methods where you just map the bottom and the top of the wall, those areas we would not have found. But because we use LiDAR and we have an insane amount of data on the side of that wall, we can create, what is essentially a surface model of the walls, the side of the wall, and we can find those abnormalities along the wall. So again, change detection and monitoring, it wasn't changing over time, but we did find areas where that wall had settled during construction. Asset management. So this is, I tie it very closely with topographic survey. But we have kind of already touched on, you can leverage LiDAR data to find assets. So if you think from a municipality standpoint, you've got a data collection project, an asset management project where you need to know where all of your fire hydrants are. Well, by utilizing let's say mobile LiDAR, you go and you mobile LiDAR the roads of this municipality. LiDAR is not biased. It's not only gonna collect the fire hydrants. It's gonna collect everything in that corridor that is above ground. And so what you can really do is we call it data mining. You may use LiDAR for a fire hydrant asset management project, but you can use that data from again, using the example of a municipality, to mine multiple sets of data from it. So let's say the next project is you need to know where all of the traffic signs are. Well, if you have already got the mobile LiDAR that you had for the fire hydrant project, you can exploit that data again for multiple projects. So again, because LiDAR is collecting all of the information, all of the topographic information, you can remine that data and revisit it and use it for multiple projects. And then here, I think I have an example of where you can see in the top left there, we've gone through and mapped out the assets on this project. Well, just like we did on the Pavement project where we export that information as shapefiles, same thing here. Each of those assets completely derived from LiDAR data can be exported as shapefiles and live inside of an existing GIS environment. I'm going to start hustling here, I promise. Condition and compliance analysis. So again, using this data, because it's so dense, You can do things like ADA compliance, where slope, cross slope, and percent slope, all that stuff is really, really important to stay compliant with ADA. It really helps if you're doing something on like a campus level, which we've done, or even a citywide level, to collect all of that information with LiDAR, and then you can do your analysis back in the office. You're not walking the streets with a digital level and a clipboard. You scan it all in one go, and then in a CAD environment, you can do your analysis at the comfort of your desk. And the last thing I'll talk on here is 3D modeling and visualization. So from the very beginning, I said I come from a very engineering-focused mindset, just because that's the world that I live in. And so from a preliminary design perspective and an engineering design perspective, engineers are being asked more and more to have more of the process done earlier on in the process. So, before you get to the end design process, clients are wanting more information sooner. And so where LiDAR comes into that is, because we're building these preliminary designs earlier on in the process, LiDAR is allowing us to generate a very accurate existing model. So if you have a really accurate, very detailed existing model, that helps you create a much better and much more comprehensive preliminary design. So a lot more of that work is happening up front, and the back half of design is getting more into the details. So the last thing I'm going to touch on here, and then we're going to have a discussion and have some questions, is some emerging technologies in the geospatial realm. So there are many, but the two I really want to touch on is unmanned systems and SLAM technology. So unmanned systems, we kind of already talked about UAS or drones. We're using LiDAR on drones. But you can do a lot more than that. So we run a pretty decent UAS program here at CEC, and what we're discovering is a lot of people want to use drones on their projects because it's the new sexy technology, right? Everybody wants to say they used a drone on their project. But the drone is not really what's important. That shouldn't be the goal of using that technology. What's really important is what the drone is carrying, the payload. What's the point of using the drone? And depending on your project, can define what the payload is. So structural inspections, I was talking to Brian and Danielle and Ollie before we got started. Last night we had a really bad storm here in Oklahoma City. That's where I'm based out of. And we've got a lot of power lines down, lots of power outages. And our team works with a service provider here in Oklahoma, and we're out right now, as I speak, with our UAS out in the field that are equipped with nothing more than high resolution cameras, not photogrammetric payloads, not LiDAR payloads. These are just drones that have really high resolution cameras that have really good zoom capabilities. And we're using those for structural inspections. In something like a storm emergency response, there are areas that are dangerous, that are inaccessible, that our inspection teams are out doing their structural inspections using a drone, right? So at a very basic level, being able to put your eyes in the sky, if you'll forgive the corniness, is very powerful. Photogrammetry. So we're all mappers here, right? We all work in the geospatial world, so we're all familiar with photogrammetry. So being able to use a drone or a UAS to generate a really high quality, high resolution orthomosaic is possible. There are commercial grade drones that can produce centimeter grade orthomosaics. Do your research if you're getting into it. Not every camera is created equal by any means. And if you have any questions, feel free to reach out to me. But I would really ask you to guard against going to Best Buy and buying a $1,500 drone and trying to create an ortho with it. There are many payloads out there, and you need to be careful. But it is possible. We talked about LiDAR already. The sensors are getting small enough now that you can fit them on drones, albeit big drones. They're not. These aren't your Best Buy drones, but the technology is getting small enough to where we can strap it on a drone. And then bathymetry. So we talk a lot about UAS, like aerial drones. But let's say you're trying to do subsurface mapping and do bathymetry. There's a photo of it there in the top left. It's called the Hydrone, and it's an unmanned system that is using that sonar technology to map the bottom of lake. Here's some just examples of some of the data sets we've collected: LiDAR, photogrammetry, some inspection photos that we've taken. But again, if you take anything from it, unmanned systems aren't necessarily new. It's not emerging technology. It's just kind of exploded. It's really taken off very quickly. And so just being smart, being diligent about the kind of UAS you buy, the payload that you integrate, just do your research. The last thing I'm going to touch on here, and then I'm going to wrap it up, is SLAM technology. So SLAM is very similar. I mean, it is LiDAR technology, and it's for indoor mapping. SLAM stands for simultaneous localization and mapping. And what it is in GPS denied areas, you can essentially hold a miniature LiDAR sensor in your hand, and it has a very finely tuned inertia measurer, IMU, and it's able to register and localize the data that you're collecting as you walk around with no GPS. So just by using the raw lasers, inertia, and an algorithm that is way too difficult for me to even try to comprehend or understand, you can generate that 3D information in GPS denied areas. This is an emerging technology. My understanding is we aren't getting the kinds of accuracies that you would expect from our conventional LiDAR methods. But if you're just trying to do something like get a floor plan of a building, then it's very, very good for that. But it's still new. It's in its infancy. Still trying to get the details hammered out. But it's one of the things that we can look forward to if you do any kind of interior GIS or interior mapping. This is a technology that I would keep our eyes on. And yeah, with that, I am done. I would be happy to take questions.
All right, everybody. This is Brian King. Let me run through some of the questions here real fast and see if we can get them. We got 3 minutes left, and great presentation, Barley. First of all, what was the viewer you were using? Is it the QT reader? Or
yes. Okay. I would ask everybody if you are interested at all in viewing and manipulating and looking at LiDAR data, Quick Terrain Reader is a free download that you can get. Just Google Quick Terrain Reader, and you can download it from the internet and install it. And if you have a LiDAR file, if you have a LAS file, there's many different types, but if you have a LiDAR file, you can literally just drag it and drop it into QT Reader, and it'll open it up.
Nice.
I use it every day. I use QT Reader every day.
Let me see here. Real quick, what is the technology a drone uses to know where it is in real time, and can it communicate with another device in real time to measure additional data? That's from George.
Good question, George. It depends on the drone that you're using. Any drone, I'm not going to say any drone, any commercial grade drone is going to be equipped with GPS. So just inherently, it's going to have GPS that it knows where it is in real time. There are drones that are more on the commercial side that are RTK enabled. And basically what that means is it's tied to what very similar to a survey base station. And so the drone will communicate with the base station, and the base station will be communicating with the satellites.
So what's a good starter drone that you have recommended to folks and colleagues?
So we are a DJI shop. If you're just getting into it for mapping, Brian, you and I were talking about the DJI Phantom 4. They're hard to come across these days, but they're very good. Their cameras are very good. They have what's called a global shutter, a mechanical shutter, which is great for mapping. So the Phantom 4 series and up, I really wouldn't go any lower than that.
And the Phantom 4 has been discontinued, but that's something you still might be able to get your hands on. Let me go one more here. We're at 1 o'clock, so let's do this one very quick, and we appreciate Bartley. We've been using aerial LiDAR locally in the San Antonio for about 10 years, and one benefit of photogrammetric surveys over LiDAR at the time was break line deliverables, something that early LiDAR collections weren't able to provide. The break line deliverables, something that is now available with LiDAR collections, are break line deliverables, something that is now available with LiDAR collections. Real quick.
Yes. Yes, period. No, it is. So the photogrammetric, the conventional photogrammetric way of utilizing it in stereo and drawing it from an isometric view, drawing in the break lines, and then what your deliverable would be your orthomosaic and your break line file. Well, kind of how I showed off with being able to extract CAD information from LiDAR, the same thing works with break line. So if you have aerial LiDAR, you get it filtered down to bare earth. You view that bare earth point cloud in 3D, and anyone who is providing aerial LiDAR data should have the ability to use what's called model key points in the bare earth aerial LiDAR data to draw in those break lines in a very detailed manner. So they should be able to deliver the point cloud and a CAD deliverable or shape files or whatever you're used to for your break lines.
Well, very nice, Bartley. We really appreciate it. We are at a stopping point here at 1 o'clock, and appreciate everybody tuning in. I think at my most, I looked up and saw about 68 people in attendance. Not sure if, Ali, I'm going to unmute you. Not sure if you actually saw more than that, but again, we really appreciate it, and we'll be posting this recording up on our YouTube channel very soon, and that is it. I hope you all have a wonderful Labor Day weekend, and everybody be safe, and we'll see you next month. And
Great.
Bartley, thank you again.
Yeah, thank you guys. Thanks again for having me.
Okay.
Thank you, Bartley.
Take care.
Take care.